This week in science, we've been talking about energy. And I told you that there's a word that we use to help us remember all these different kinds of energy that we talk about. We use that word melts. MELTS. Each one of those letters stands for a different kind of energy. M stands for one kind, the E stands for another, the L for another, the T for another, and the S for another. Who can tell me what is one kind of energy we've talked about this week? Violet, what's one kind? Mechanical, very good. That was the energy of like our muscles moving or of parts of a machine moving. Jadine, what's another kind of energy?
Sound.
Sound energy. So waves that go through the air and they go into our ear, and that's how we can hear. What's another kind? Noah?
Light energy.
Light energy. What we can see, right? Comes out of the sun or like out of a lamp or a flashlight so we can see things. Brianna, what's another kind? We said mechanical, sound, we said light. There's two more left. Hearing is the sound energy. We hear that one. Travels in waves. We can't see that one, but the light is the one that we can see. What's another? We talked about the mechanical, so the M. We talked about sound, that's the S. We talked about light, that's the L. So we're missing the E and the T. What's the E kind of energy and the T kind of energy? Alexa, what's one of them? Thermal energy. What is the thermal energy? Do you remember? No. No, not exactly. It can be. It can work with the light. T, the thermal energy, is heat, the temperature. So the more thermal energy you have, the hotter it is. The less thermal energy you have, the colder it is. So something like a cup of coffee or hot chocolate in the morning has more thermal energy because it's nice and warm or hot, and something like a milkshake would have less thermal energy because it's nice and cold. Jaylene, do you remember what the last one is? The kind of energy that starts with an E?
Electrical.
Electrical, very, very good. The kind that we use for our phones, for batteries, for our computers, for a lot of things. Electrical. Okay, today we're going to focus on electrical energy. We're going to talk a little bit more about that, the way electricity works, and some very important things having to do with electricity. Yes, Alexa. A test on electricity? No, we have a science test tomorrow, but we don't have one today. Okay, so we're going to watch a video. So make sure that everyone has their microphones off. Make sure that everyone has their cameras off so that we can hear and that we can see the video. And let me share my screen. First, let me find the video. Okay. We're going to watch this video over electricity. And I'm going to stop it at certain points and we're going to talk about different things that the video says for us or has different information that it has for us. Christopher, make sure we have our camera officer. That way we can watch the video nice and clearly.
Makes this happen. This. It's electricity.
Science rules. Inertia is a property of matter. T minus 7 seconds.
Brought to you by Electron, making your world
Okay, so yesterday I mentioned about electricity and how it was made by moving electrons. So electrons, you can't really see them, and they're going to talk a little bit more about them later on. But when they move, that's what's creating the electricity. And we can kind of see this picture that's showing up of a ball, and it's got little like arms of electrical energy kind of coming.
Is your TV on? It is. That's great. You're using electricity. Is it just the wall? Use it? Notice. They're not just smaller than part of it. Take a look at the word elective. This side, through this, through the switch, to the light, back.
Okay, so I want you to take a look, and they've kind of shown us what's going on inside of the wire here. But once he goes ahead and he flips that switch, we can see that the electrons go from one side of the battery, from the negative side. He's using a big car battery, so it's easier for us to see. But it goes from the negative side of the battery, and they start to move. And they move through the wire to the switch. They go through the switch, so they would go up this side, they would go across, and then down this side. So this is kind of like a bridge for them. They go through another wire, they go into the light, and they leave the light, still going through the wire, and go back to the battery, but this time to the positive side. So it all makes one big loop. We call that a circuit. And I want you to notice that earlier, when he first showed us this light, and even though everything was already hooked up, it's not on. But look at his switch. The switch isn't touching the other side. If this switch, if this piece of metal here doesn't touch the other side, then those electrons have no way to cross from this side of the switch to the other side. So the electricity can't move right now. It's kind of stuck on this side of the switch. It's got no way to get over. Once he actually moves the switch down, then they have a way to get over to the other side, and they can start moving.
From this side, through this wall, through the switch, to the light, back. Electric. So electric. Go.
So the same thing happens in our houses, in our rooms. When you go into the room and you turn on the light switch and the light comes on, you're doing the same thing. Now your light switch looks different than the one that he has, but it's doing the same thing. It's giving those electrons a way to go around a circuit. And like he says, they want it to be what they call a closed circuit. If it's closed, that means there's no breaks, there's no stops, there's no gaps, there's no openings. So that way the electrons have a way to go all the way around the circuit without being stopped. If there's an opening or a gap or a break somewhere, then they're kind of stuck on one side of the circuit and they can't move.
Of water. Right, this great science. Water goes through this hose. into this box, water goes out the other side, goes back to the pump. It's a closed the flow of water. It's a water circuit, just like runs through. Making a motor go electricity through all different. They're all done with electrons.
And they brought up a good point there about the flow of electrons. And the kid compared it to like water going out of a water hose. So if you've ever noticed that sometimes there are some chargers or some cables that if you use them to charge your phone, it seems like your phone takes forever to charge. And sometimes you might use one cable or one charger that it seems like your phone charges super quickly. Yes, Jadine.
My mom, like, she has this phone that has a phone super quick. That it doesn't.
Yeah, some of the cables or some of the chargers charge very quickly and some of them don't. It's because, like in this example, he tells us about a water hose. If you have a cable or a charger that lets a lot of electrons go through, your phone can charge a lot quicker. If you've got one that only lets a little bit through, then your phone will take longer to charge. Yeah, and sometimes, Messiah, usually the charger that comes with your phone is the one that works best with it. It's the one that will let it charge the fastest. And if it breaks or it gets lost or anything like that, sometimes you buy another charger and your phone will still charge, but it takes a lot longer now because it's not letting as many electrons get into your phone. We can see there with all that water, it's spinning that little thing they have around pretty fast. And it's been this big one around, so it makes it look like it's moving. Okay, I like this example. Bumper cars. Real quickly, just you can raise your hand, you can type me in the chat, but I want you to raise your hand or type me if you've ever ridden on bumper cars. Like at Western Playland, at any place that has bumper cars, if you've ever been on bumper cars. Cool, so there's a lot of us. Okay, so for those of us that have been on bumper cars, yeah, it can be pretty fun. You know that when you first go in, you walk around, you find your car and you sit down or you start driving it around, right? Like he said, all the bumper cars, they run on electricity. You don't have to put gas in them. They don't have tanks that you have to go and fill them up. They run on electricity. But those of you who have been on the bumper cars know that when you walk out to get into your car, you don't get shocked or anything because you stood next to the bumper cars. And he's going to explain it here, but you notice behind him and behind the other cars, they've got this big metal pole coming up out of the bumper cars. And you can see this one, the pole goes all the way up to the ceiling. And he's going to talk about it a little bit here. The pole goes all the way to the ceiling. The reason why you don't get shocked when you walk out to get into a bumper car is because you're not touching the ceiling. The electricity, remember, has to have a closed loop, a closed circuit. It has to have a complete path to move. If there's any kind of break or gap or open space, it can't move. So because we're not tall enough to touch the ceilings, the electricity can't get from the ceiling down through the wire and into the car. And then it goes from the car and it goes round, so that way it can complete the circuit. It has to make one big loop. But because we're not touching the ceiling, we don't get shocked. And since the cars are touching the ceiling, they're able to have the electricity go through. Well, the wheels on the bottom help it move around a lot easier, Messiah, but if it weren't for the electricity and it just had wheels, they wouldn't just move on their own. The motor, instead of using gasoline like how the motors in our car use gasoline, these use electricity to make those wheels move. And he'll show you right now. See, so like you said, because we're not tall enough to touch the floor and the ceiling at the same time, we don't get shocked. And I want you to see, when he first gets in, you'll see a little spark between the wire and the ceiling. Look, you see him right there? I know it's really small. But right where the wires at the back of the bumper cars meet the ceiling, you'll see little sparks, because that's the electricity going from the ceiling down the wire and into the bumper car. That way it can actually move around. Yeah, we can't see a whole lot of it. Usually you don't want to see electricity. If you see electricity, you know, sparks and stuff like that, it's usually not a good thing. See? We can see them again there when he's talking about the rod in the ceiling. And we get a little bit of a better look that time. See, so as the rod is going across the ceiling, you'll see little sparks because the electricity is going from the ceiling into that rod, that wire in the back, and it goes and it connects to the motor in the bumper car. That way you can actually drive it around. Like he says, it has to be a complete circuit. So once it leaves the car, it leaves through the bottom, it goes through the floor, and then it goes back around using these columns that are in the corners, the ones that hold up the ceiling. It goes back up through those and then back into the ceiling. Yeah, people having their cameras off helps a little bit, but it might still be a little bit laggy. But that's okay. That's why we're pausing every now and again. Just to make sure that even if we don't get to hear the way he explains it, we can still talk about it. Those ones with the number, Messiah, those are probably go-karts, not bumper cars. They look kind of similar though. So this is useful to know. Like it says, if you have batteries, if you store them in the refrigerator, it helps them to last a little bit longer. Doesn't mean that we should fill up our refrigerator with batteries, but it can help them. Yes, Alexa. Oh no, those are different ones. So the bumper cars are the ones that have that big wire that comes out of the back so it can connect to the ceiling and so they can move around.
Oh, okay.
Hey, so check that out. When you go to the store like Walmart and you see the different light bulbs, the 10-watt light bulbs, it's the same amount of power that your brain uses. This one's important for computers and for phones and things like that. If you've ever noticed that when you're using your phone, like if you use it for a long time and you're watching like lots of YouTube or you're playing a game on your phone and your phone starts to get real hot, And sometimes when it gets really hot, your phone kind of like slows down. Like if you're playing a game or something like that, your phone like it might look kind of laggy when you're playing, or like your computers when you use them, and if you're playing games or if you're watching a lot of YouTube, they start to get really warm. They don't tend to work as well because cold metal lets the electricity go through faster. Lets it go through better than hot metal does. It's okay. So like he said here, the wall sockets, we have to be very careful with them. Usually we learn more as like little kids when we're really young that you shouldn't stick anything into the wall sockets unless it's a plug. It's the only thing that goes in there because there is a lot of electricity that flows to our house and there is enough there to seriously hurt you. So we only put in wall plugs into them. What's up, Violet?
Electrocuted.
Yeah, it's if you get shocked or things like that, it's not a very fun thing to have happen. So we
Restart.
Yeah, so we want to make sure that whatever we put in there, it's only plugs, only things that belong in the wall sockets. And it doesn't matter how big or how small it is, whether it's this size or whether it's this size. So if you've ever seen or you've ever played with these electrical trains, they make a circuit too. And like she mentions, the train has two different rails. Let me see if I can pause it in a part that shows you a little bit better. There we go. So it's got two rails, two strips of metal. The electricity has to go through one side, then it goes through the wheels of the train, into the train, and then back down the other side. And that's how the train is able to move. If you've ever had an electric train or you've ever played with one, you know that if something bumps the train and it's not touching both of the rails, then it doesn't move. It just sits there. You have to make sure it's on both of the rails before it will move.
Moved it. He did.
So you notice how he's got both of these coils, both of these like circles made out of wire, connected with wires here in the middle. So as he's moving one, we can kind of see that wires are coming out of it and connecting it to that other circle, that other coil of wire he has. So with this experiment, we're able to see that magnets or magnetism and electricity kind of work with each other. That's why if you have like your phone or a TV or a computer, you have to be careful when you have magnets. You don't want to put them too close to the computer or to the computer or the TV or whatever you might have, because sometimes they can mess with each other and they can mess it up. I think that the TVs that they make now are a little bit better about this, but I know especially like the older ones, if you put a magnet too close to them, you can actually mess up the TV screen. In fact, when me and my sister and my brother were younger, we got in big trouble with my dad because he used to have these big magnets. They were very strong magnets that he had on the refrigerator to hold up, coupons and stuff like that for different places. And one time we took the magnet and we noticed, hey, when you put the magnet on the TV, it made these really cool colors. Like it changed the colors of the TV screen. And we didn't know we were messing it up. We just thought it was cool. And we put it on there for too long. And even after we took the magnet off, all the colors on the TV screen were messed up. So don't do that. That is not a good idea. It's a very expensive idea. Don't try it.
He did. Other core. Will you tell me use newborn that was with no be a
But like you said, it was pretty cool, pretty amazing to them that they figured out something's going on. There's some kind of energy happening here. And what made it even more impressive is that they couldn't see it. Usually if something's going to move, you see something happening to it. If your toys move in your room, someone's picking them up, moving them somewhere. But they were able to do this, and like you said, the compass needle moved without anybody going over there and poking at it or anything. So they knew something was happening, something was making it move, but they didn't know what it was. And they couldn't see it, so they were trying to figure it out. It turns out it was just electricity. So this car is an electric car, but what makes it even more impressive as far as being an electric car is that if you notice, it's got all these little tiny black rectangles all over it. Those are really small little solar panels. So this car, if it's sitting out in the sun, can get electricity just from being out in the sun, and it's able to move around using that. We saw in the bumper cars that they needed to have the poles that go up to the ceiling so they can have that circuit for the electricity to move through. But this car wouldn't need that big wire. It could just have light shine on it. It could use that to make its electricity. Look at that, 1,400 of those little black rectangles that they put on this car just to make sure that they could get as much electricity for the car to run as possible.
electricity is roll.
I want you to look at that. Look at how they connected all those batteries for this car. So look at all those. Those are all batteries. And you notice how they have wires connecting the batteries from the first one to the next one to the next one to the next one. They wanted to make sure that the electricity was able to flow from one battery to the next battery after that, and the one after that, and the one after that. So they had to make sure to put wires in between them so that the batteries could let the electricity keep moving.
go.
Okay, so he's talking about different materials. And we have an example here. Two thin metal rods, and they're passing electricity through them. We're able to see little arcs of electricity kind of connecting them as it goes around. Like we said earlier, and like we saw earlier, the electrons need a place to go. They need a path to follow. If there's a gap, if there's a break, if there's an opening, they can't follow that path. But there are certain materials that let those electrons move, that they kind of help them to move along. And he mentions metal, and he shows us these big like sheets of metal here. See if I can get a good picture on it. So he's got like these sheets of metal here. Metal is a really good conductor. That means that it lets the electricity go through it. Conductors also let heat go through them. So if you've ever noticed that, like in the kitchen, the pans that people use to cook, they're pretty much all metal. There's a few other pans that might be like clay or something like that, especially if they're gonna bake, they might use glass. But a lot of the pans that people are gonna use for a lot of cooking, the pans that we put on top of the stove, they're metal pans. Even some of the pans we put in the oven are metal pans. We use metal to help us cook because it lets electricity and it lets heat go through it pretty easily. So the heat can get from the stove to your food, or like in this case with electricity, it lets the electricity go from one side to the other, and it doesn't really slow it down that much. It doesn't try to stop it. It just lets it go. It gives us the examples of bees and beehives. Because of the way that metal is made with the atoms, the bees, or in this case the electrons, are able to go from one to the other very, very easily. They don't have a hard time. So electricity can flow pretty well in metals. So we can see that they've got a battery, it's hooked up to a light bulb, and they've got wires. So they're going to use the wires and touch different things, and we're going to see if it lets the electricity go through. If the light turns on, then we know the electricity can go through that. If the light doesn't go on, then we know the electricity isn't able to go through whatever they're touching. So we can see that with the spoon. Once they touch the wires on the spoon, the light turned on. Because again, the spoon is made out of metal. Metal lets electricity go through really easily. They tried the tennis ball. The tennis ball is made out of rubber, so it bounces when people hit it. Or when they, bounce it up against the wall or something. Because it's made out of rubber, rubber doesn't let electricity go through. It stops it. So we noticed that when they touched the rubber ball, the light didn't turn on. Okay, here they have a plastic pen. They tried the same thing, and again, it didn't work out. Plastic doesn't really let electricity go through it very well. That's why when you're holding your phone, they'll have like plastic or rubber, especially if they're using phone cases. They have the plastic or the rubber on the outside, so that way when the electricity is going through your phone, when you pick it up to answer a phone call or to text somebody, you don't shock yourself by accident. Because the electricity won't go through the rubber or the plastic on the phone. Oh, see, they have another thing here, like a mixer, and they have on the what they call beaters. They're made out of metal, and again, when they touch the metal parts with the wires, the light turns on right away because the electricity is able to go through it again. So notice what's going on there. They tried to connect the wires to the wood part of the pencil. And the wood part didn't let the electricity go through. Stopped it. The light bulb didn't turn on. But when they split the pencil in half, they cut it open, and they used that pencil lead, that graphite in the middle, we can see that the light turns on, but it doesn't turn on all the way. It turns on like halfway. So it's letting some of the electricity through, but it doesn't let all of it through. So conductors are things like, again, metal is a really, really good conductor. That's why a lot of the pans that we use to cook are made out of metal. It's why the parts that they use to make phones and computers and TVs out of are made of metal. It's a really good conductor. It lets the electricity go through very well. And insulators, like he said, do not let the electricity go through. So things like plastic, we saw rubber, and wood. Wood is another insulator. So all those keep the electricity from going through them. So the inside of that pencil lead, they call it a resistor because it kind of does a little bit of both. It lets electricity through, but not all of it. So it's not really a conductor, it's not really an insulator, it's something in the middle, something in between. So they call that a resistor, when it lets some of the electricity through, but not all of it. So he gives us a pretty good example there about how much electrons or how many electrons are letting go through at one time. And he gives us the example of a water fountain. In a water fountain, sometimes you press the button and the water comes out, and sometimes you press it and the water is like barely like dribbling out of the water fountain. Okay, make sure we have a camera off.
Sorry, I had to leave because those like
So the same thing is true about electricity. You have pressure and you have flow, but they use different words for it.
the voltage. Because it does.
So voltage is what we call the pressure when we're talking about electricity.
Higher the voltage.
So he's got there two different light bulbs. And you'll see this when you go to any store that sells light bulbs. They'll have on the side of the light bulb, it'll say it'll say things like their wattage or their voltage. You have to make sure that when you buy light bulbs that you buy the correct voltage or the correct wattage that they have on there to fit your lamp or your ceiling fan or whatever. If you ever try and use a light bulb that, let's say, uses less volts than what your lamp or what your ceiling fan uses, you can actually just burn out the light bulb or break it or even damage your lamp or things around your house. So you have to be very careful, because it's like putting too much water into a water balloon. It'll just burst it. But in this case, it's with electricity. So you need to make sure that when you buy light bulbs or things like that, and you can see them the next time you go, or if you have a pack of light bulbs hanging around the house, you'll see them on the side. It's okay, Messiah. You'll see them on the side. It'll have a label for how much wattage or how much volt the light bulb is able to use safely.
Drinking fountain. Two things. Voltage.
So like he said, amps in electricity is like how much electricity there is. So some things can handle lots of amps, some things can only have a little bit. Kind of like having a big glass and a small glass.
The combination. You know.
So he's got two light bulbs here. One's 100 watts, one is 40 watts. And you notice the 100-watt bulb is a lot brighter than the 40-watt one. Now, you can also see he's got these little pieces of plastic here. That's what's helping the electricity get into the light bulb. But you can't just buy, if you want your lamp or your ceiling fan to be brighter, you can't just go and buy a light bulb that needs more watts. You have to make sure that it's one that will work with your light, with your lamp or with your ceiling fan, because again, if you get one that uses a different number of watts, then you could break the lamp, the light bulb, or both. Or sometimes, depending on what goes on, it could even break and you'd have broken pieces of glass or things like that all over your floor, and you definitely don't want that, especially if you've got little brothers or sisters or dogs running around the house.
Connected to the side. We're running.
We talked before about like how we make electricity, and we talked about power plants and things like that. And I told you, when they make electricity, they use these big generators, and they have these things inside that just turn over and over. They're spinning like in a circle. And that's kind of what he's got hooked up to that bicycle there. So as he's pedaling and the wheels are moving around and around, he's spinning that generator, and you can kind of see it here on the side of his bicycle. He's spinning the generator, and when the generator spins, it makes the electricity for that light bulb on the front turn on.
I mean, because those kids.
So again, we can see the circuit. We can see it starts here at the negative side of the battery, the negative pole. It goes down through the wire into the light bulb. And it leaves the light bulb going through a different cord, a different cable. And it goes to the positive side of the battery. That's why when you put batteries into your things, whether it's a flashlight, whether it's anything, when you put them in, you have to make sure, usually there's one side that has like a spring on it and the other side is just kind of flat piece of metal. If you don't put your battery in right, if it's kind of sticking out or it's sideways, whatever it is won't turn on correctly because you don't have metal touching both sides of the battery. And if it's not touching both sides, if one of your sides is disconnected, then you don't have that complete circuit. You have a break, you have an opening, and the electricity won't be able to flow.
Yeah, chemical used up. These are good. Careful.
So really quick before they show us this, I want you to either raise your hand or you can type me into the chat if you've ever heard of electric eels. Okay, so some of us have. So they're going to show us a little bit about these electric eels. These eels have things inside their body that is actually able to create electricity. So they use it when they're going around hunting and trying to get food.
Bad. From it's a lot.
So right now they're going to show us a power plant that's inside of a dam where they make electricity for people's houses. But I want you to remember really quickly, think about how small, and I'm going to go back and show you. Look at how small this generator is. This one next to his bike. Okay? He's going to show us one that they use at this dam to make electricity for people's houses. And I want you to see how much bigger it is. I'm sorry about that, Brianna.
Ran is behind front. Really huge. Big.
Kind of, Messiah. So the water starts on one side of the dam where you can see where the water's a lot higher, and then it falls through. And when it falls, it spins these big turbines. And you can see here, I know it's a little bit darker in the background, but let me see if I can pause it.
Really.
There. These are the generators inside that dam. So we can see just how much bigger they are compared to the ones that he had on his bicycle. And if you're wondering how big they are, this is a person standing next to one of them. That's a full-grown person, a full-grown adult, standing next to one of these generators. So you can see just how big they are.
Big.
Probably not.
Upside down.
I'm gonna try something real quick, Brianna, because you said it was lagging. I'm gonna try playing the video like this and see if it helps us for those of us who have it lagging a little bit.
Alternating
But like you said, when we talk about electricity, there's two main kinds of current. There's AC and DC. So AC is alternating current, and that's like the crank that he was using. Let me see, it was back here. So as it's spinning, like you said, it goes one way and then the other. So they call it alternating current. If we're using batteries for electricity, then it's only going in one direction. So we call that DC, direct current, because there's just one direction for it.
down.
Okay, so I'll leave it like this. We saw a picture of these the other day. These are solar cells. So you can see that they all kind of sit on these big panels, and they're kind of angled up, and they leave them out in these big wide open areas. And you'll notice there's no trees or anything around, because if there were trees, they would block that sunlight. And as the sun hits these photovoltaic cells, these solar cells, then it's able to turn that sunlight into electricity. Raise your hand or you can type me into the chat if you've ever seen birds sitting like this on power lines. All right. So you'll notice, like in real life and here in this picture, these birds, even though they're standing right on power lines, they're not getting shocked or anything like that. Because remember, electricity has to have a path to go through, has to have a circuit. If it doesn't have a path or a circuit, it doesn't flow. So these birds, if they're only touching one of the wires, like we saw with the electric train earlier, they don't have that circuit for electricity to go through. See, and he gives us the example of like the science fiction movies like Godzilla. When the two wires on those power lines, when they touch, that's when you see those big sparks and stuff, because the wires, since they're touching, are creating or completing a circuit, and the electricity is allowed to go through, and that's when you get those sparks. Like on the top of the poles from the bumper cars. When the poles are rubbing against the ceiling where the electricity is coming from, they have those sparks. Same thing is happening here. When those two wires from the electric lines cross, or when they touch, they create sparks because now they've completed a circuit and electricity is able to flow through it. So like she said, when we have light switches, or like on the flashlights, it has that button. When you turn it on, you're making sure that you complete the circuit. You're giving the electricity a path to go through. When you turn it off, you're breaking it. You're opening the circuit, and you're making sure the electricity doesn't have anywhere else to go. So it's just kind of stuck. It can't move.
Coming. This movie that in your space.
So take a look at this and notice all the things that we use all the time, every day, that have batteries or that use batteries.
World without
So if you ever wondered why when you plug something in, the plugs for that thing, whatever it is, your computer, your phone when you're going to charge it, in this case he has a blender, they always have two prongs, at least two. Sometimes there's three, but they all have at least two metal prongs. And like you said, the reason for that is because electricity has to go in a loop, has to go in a circle. So one prong is for the electricity to go into whatever you're plugging in this case is blender. One prong is for the electricity to go into the blender, and the other prong is for the electricity to come out of the blender. If there's only one prong, you won't have a circuit. The electricity won't go through, and whatever you're using or trying to use won't work. So if you have one that's like really old, like in this case, if this blender was pretty old and one of the prongs breaks off, you wouldn't be able to use it anymore because you wouldn't have a loop for the electricity to follow. So when he pulled that switch again, he made an open circuit. There's an opening, there's a break, and the electricity isn't able to flow. So all the lights start to turn off one by one. All right, that's the end of that video. So we can go ahead and turn our cameras back